Hi, I'm Alistair, and in this video I'm going to explain how you can create your own large modular 7-segment LED displays, like this one. Now, there are loads of projects that need some sort of timer or countdown, and if you only need a small display, you might use a module such as this. Now, this has already got an LED driver chip on the back of it, which means it's very easy to control directly from an Arduino or a Raspberry Pi. But the problem is it's pretty small. Now, if you wanted to make a larger display, you could create one using individual 7-segment digits, such as this one. But this doesn't have any of the additional control circuitry, so you're going to have to combine it with some sort of driver, perhaps the powered transistor output from a shift register, and then you're going to have to worry about things like whether it's common anode or common cathode configuration, multiplexing, things like that. None of which are individually that complicated, but they're just a hassle. And these digits themselves are not that cheap. So the approach I took was to create something that was easy, was cheap to make, and was scalable to a large size. And what I did was I've created this display using a programmable LED strip such as this. So this is a WS2812B or Neopixel display. And I've simply coiled it around into the shape of the digits of a 7-segment display here. Then I've got an Arduino which is controlling which sections of the strip to light up to correspond to each of the different segments, and that can make any digit appear. Now, the advantage of this approach is that it is running solely on 5 volts with a single data line from the Arduino. It is infinitely scalable to almost any size because you simply use a longer section of LED strip. And because this is an RGB strip as well, it means that you can create the time display in any colour you want. And in this video, I'm going to show you how I made it and how you can make one yourself. So programmable LED strips like this have become very common in electronics projects, but just in case you're not familiar with them, I'll briefly describe how to use them. So they come supplied on a reel, and you can simply unravel the strip from the end. You can see the separate LEDs are spaced out regularly along the strip, and in between them there are these copper connections. So when you want to cut a strip down to a particular length, you can simply cut across a set of those connections using a pair of scissors. And you make sure you cut straight across the middle of the connection so that you have exposed copper contacts on both the cut edges. And what you can do is cut several of these strips and then lay them out into the shape of a 7-segment display, then solder wires between those cut copper contacts on the corners. Now, one thing to mention is that the strip does have a direction, which is indicated by the arrow here. So there's a data into each LED, and then there's a data out that goes to the next one in the strip. So if I unravel the whole strip, we can actually trace it right back to the start. And here you can see we've got the first LED in the strip, and it's got a 3-pin JST connector. And it's also got 2 other wires here as well. So the JST connector has got ground, 5 volt and a data line that comes from an Arduino or other controller. And then there are also this other pair of wires here, and they are simply additional wires for the 5 volt and ground line. They're just there to enable you to easily connect an external power supply. Now, most microprocessors can't connect directly to a JST connector, so what I generally do is make a little adapter board like this. As this has a female JST connector which will connect to the LED strip, and then it also has 2 components on the board. There's a 470 microfarad capacitor here, and then underneath there's also a 330 ohm resistor in the series on the data line. Now, you might find that your LED strip will work fine without these additional components, but it's good practice to add them. And then I've just got the 3 wires here, which I can connect directly to the Arduino. And now the last thing to mention is just about LED density. So the first strip I showed you has got 30 LEDs per meter. And then this black strip underneath here has got 60 LEDs per meter instead. So you can see there's exactly 2 for each one in the LED above. Now both strips work in exactly the same way, but having a higher concentration of LEDs will make the strip brighter and more uniformly distributed, although it will also mean it will draw more current as well. So that's when you might need to use that additional secondary power supply I showed you with the 5V and ground connections, rather than trying to power the strip directly from the Arduino. So now let me demonstrate the display I was using at the start of this video in a bit more detail. So this is 3D printed, and if I pull the cover off one of the digits, you can see the components underneath. Each segment has one of these covers on it, which is printed in transparent PLA. And you can see it has 4 recesses on the side here, which line up with the 4 LEDs in the strip in this segment. And these covers hold the LED strip in place, and they also act as a diffuser to spread and soften the light in each segment. So if I just pull the rest of these off, now you can see that the LED strip enters the digit through these wires here, and then it goes across the middle segment, up, across the top, and then down, all the way down this side, across the bottom, and finally up again before exiting the digit just here. Now, unlike in the previous example, I've not cut the strip into separate segments. This is all one continuous strip of LEDs. So I can actually pull it out here, and you can see that it bends around the corners, and they line up with the copper breakpoints between LEDs. So there's no stress on any of the electronic components, and you can just push it down into the frame so that exactly 4 LEDs lie in each segment. And you just follow it all the way around the digit like this. Now, one more thing to note is that there is an LED in the middle of the left-hand side here, which is not part of a segment. So that will never get lit up. And that might not sound very efficient to have an LED that's never used, but the benefit is that you can have a single strip that's threaded through the entire digit with no need to cut it into segments. So I think it's probably worth the trade-off. Now if I just place these segment covers back in place to hold the strips in position, and then if I put the cover back on as well, so that just seals the unit back up. And then all I need to do now is to turn the power back on, and you'll be able to see those diffusers in action. And I'll include a link to the STL file of the 3D model I'm using for each digit. It was originally based on a 4-digit display model, which was on Thingiverse, but it's been modified so that it's just a single digit. It's about 8 inches high. And this just makes the design much more modular, because you can print only as many digits as you need. If you only want a 2-digit or 3-digit display, or if you want an 8-digit display, you can simply print more of these models and stack them side by side and thread the LED strip through it as many as you want. Now you could use this display to show any numeric data you wanted. It could be the high score from a game or a stock price, but I'm guessing the most common application will be some sort of timer display. So to demonstrate that, I've written a small Arduino code with some basic timing functions, and I'm going to demonstrate it in action first, and then I'll show you the Arduino code in a moment. So when it first loads up, the display shows 0. If I press this button in the middle, it's going to start a counter counting up, and the display will simply show the number of seconds that have elapsed. If I press the button in the middle again, I can pause that count up, and I hope this comes across on camera, but the colour of the display has changed slightly. When the counter is paused, it kind of pulses from yellow to red. If I continue the count up again, it changes to a solid red. So that's just one way you can use the RGB nature of the LEDs to kind of give a visual indication of what the state of the counter is at the moment as well. Now to reset the counter, you can press this button on the left, that will go back to 0, and then if you want you can start a new count up again, so you can do that as many times as you want. Now as well as having a count up, you might want to have a count down function as well. So to set the duration of your countdown, you press the button on the right, and this is going to set a value in minutes and seconds. So that would be a 4-minute countdown, for example. That would be a 1-minute countdown. Now, I've chained 4 digits in a row here, which I've configured to be minute, minute, second, second. But you could add more digits onto the end. So let's say you want to record tenths of seconds or hundredths of seconds, or maybe you need a counter that has hours as well. That's fine. You can make this chain as long as you want. As I said, this is essentially an infinitely scalable display. So each of the digits can have as many LEDs in them as you want, and then you can have as many digits as you want as well. That's all configurable in the code, which I will show you in a moment. And here's just a quick diagram to illustrate how I've got those components wired together. So I've got my 3 buttons, which are wired to GPIO pins 4, 5 and 6, and then to ground on the other side. And then I've got my LED strip here, which has got a 330 ohm resistor in series on the data line going to GPIO pin 2. And then it's got a capacitor across the ground and 5 volt lines, which are also going to the Arduino here. And then this LED strip here, I've just tried to illustrate the fact that I've got 4 individual sections of strips, 1 for each of the digits, and they are wired together here, so they've just been joined into a single long strip again. So now let's step through the Arduino code. So this is a single sketch that contains both the functionality for the LED display and also for the stopwatch and countdown functions which I demonstrated. Now if you want to alter that behaviour, or if you want to use the display in a different way, you can just delete or modify those sections of the code accordingly. So starting at the top, there are 2 external libraries which I'm making use of. The first is the Fast LED library, which is a very good library for interfacing with all kinds of LED strips. I'm using WS2812B, but if you're using a slightly different kind of programmable LED strip, there's a very good chance that this library will support it as well. I'm also using the Bounce library. That's just a really useful library if you have any kind of mechanical button input. It just helps getting a clean signal from those buttons without the risk of you accidentally getting double presses or something like that. And then I define a couple of values here. So the first one is the number of LEDs which I'm making use of in each digit of the display. You'll see that that's 29, which might seem like a bit of a funny number. So just to remind you how I've got those strips laid out, I'm first going across the middle of the strip, which is 4 LEDs, and then I have 4 for each of the subsequent segments. But on the left-hand side, between the 2 vertical strips, there is 1 LED which is not being used at all. It sort of lines up with the gap between the 2 segments on the left-hand side. So I've got 7 lots of 4 LEDs and 1 extra. That's how come I get to 29 in each digit. And I'm using 4 digits in total, so that gives me a total number of 116 LEDs in the strip. I'm using GPIO pin 2 on the Arduino to send the data signal, and I'm also using the double minute, double second display, as I mentioned. If you would like to use a 4-digit second display instead, so you get thousands of seconds, hundreds of seconds, tens of seconds and seconds, you can comment out this line here, and instead it will just show a total in second values. That will come later on in the code, how that's used. Then I define a couple of constants. Now, this is going to vary depending on exactly how you've laid out your strip, because the array which I define here has the 0s and 1s corresponding to unlit or lit LEDs in the strip, corresponding to each digit that you want to display. So I'm using a 32-bit integer because I've got 29 LEDs in each digit, and I need to have a value that's capable of storing 29 ons and offs for each digit. Now, if you were making a larger display that had more LEDs in each segment, you might need to increase this to a 64-bit integer instead. So you'd simply change the variable there to 64, and then you could have another 32 zeros and ones on the end. But generally speaking, you want to use the smallest data type that is capable of storing all the information you need it to. I've got 29 LEDs in each digit, so I'm using a 32-bit integer. So there are 32 zeros and ones in each of these strings here. The 0B at the beginning shows that this is a binary value. The 3 zeros here, well, that's because these are kind of padding essentially, because I'm only going to make use of 29 LEDs. So these are just padded at the beginning with 0 because they're always not going to be used. And you'll notice that there is a 0 in each position here in every string. That is the LED that is on the left hand side that we never want to be lit. All the other values here are in groups of 4 corresponding to the 4 LEDs that are in each segment. But the order in which they are listed is going to depend on the way in which you threaded your LED strip through your digit. So remember, I went across the middle, so I've got G, then B, then A, then F, then E, then D, then C. So the way that I've written out all these numbers here goes G first. These are the 4 LEDs that go across the middle of the strip. And then I'm going to go 4 LEDs that are in the B strip, which is at the top right. Then A, which is across the top. And then going down the left-hand side, that's my gap. And then the bottom left, and then the bottom, and then the bottom right. So in this case, that is the string of ones and zeros that represents the digit 0, because all of the segments are lit except for the very first one, which is the one across the middle, and also that one that is on the left-hand side, that single digit display. If we look at the digit 1 instead, you'll see here, I've got my 3 padded zeros at the beginning, so they don't do anything. And the only LEDs I'm lighting here are at the top right-hand side. That's these 4 zeros here. And then these ones at the very end of the strip here, these are at the bottom right. And that's how you form the digit 1. So, I mean, you can make any shape you want, really, these patterns here. These just correspond to each of the individual LEDs in the strip. And you don't even have to have the same number of LEDs in each segment. If you wanted to generate a kind of a tall, thin digit that only had 2 LEDs in the horizontal segments, and maybe it had 8 LEDs in each of the vertical segments, that's fine as well. All you need to do here is define the pattern that specifies which LEDs you want to come on for each digit. Okay? Then we get onto some more constants. So these are just very simply the pin assignments that we connect each of the buttons to, 4, 5, and 6. And we create some global values, which are going to be shared throughout the rest of the code. The first one is our global array of LED values, and that is going to have a number of LED elements in it. So remember, we define that at the top of the code. That's equal to the total number of LEDs in the strip. It doesn't care at this point what digit they're assigned to. You just need to initialize the fast LED array so that it has one element for every LED, even the ones that will never get turned on. We initialize 3 bounce objects as well. So these are going to be button inputs, which correspond to our left pin, our start pin, and our right pin. If you are familiar with Arduino code, you might be used to using digital read, and you could just do a digital read of each of the pin numbers here. That's fine, and you can do that. As I mentioned, the reason I'm using the bounce library is that when you have any kind of mechanical switch and you first press it, you literally get bouncing of the contacts. The metal pins that come together can kind of click together and then come apart and click together a few times, and you end up with a slightly noisy input signal. So the reason for abstracting it slightly and using this button class, although it might make it seem a little bit more complicated than a simple digital read, is you get more reliable input as a result. Now the next values here, so these all relate to the use of the timer and the countdown functions. So you only need these if you're actually wanting to display a time value. If you want to use the display for something else, don't worry about this too much. So I'm going to keep track of the time at which the counter started counting. And if we are using a countdown function, I'm also going to have a variable that keeps track of the value we're counting from. So in my other example, that was going to be 1 minute. Now these are both saved in millisecond values. So actually, if I did want 1 minute, this would be equal to 60,000 because there's obviously 1,000 milliseconds in a second and there's 60 seconds in a minute. And this is the value that gets increased when you press the right arrow in my little demonstration. Now, because I allow the user to pause the countdown or count up and then resume it again, I also need to keep track of effectively all of the previous elapsed time that has happened when the counter has been in operation. So in a given kind of session, as it were, I work out how much time has elapsed based on the current time less the time at which its session started. That's the current time. But then I also need to keep track of every subsequent time the timer has been started since it was last reset. So that's what the cumulative elapsed time does. We've got a couple of enumerations. So we keep track of whether the counter is currently active or not. So this is whether it's changing value. And if it is changing value, we need to know whether we are currently counting up or counting down as well. Then we get onto some functions. So this first function here, this relates to assigning values into that LEDs array, this one here. So this is recording one element for each LED in the entire strip, and it's going to give the RGB value that we want to give to that LED. Remember that the array here told us which LED, it's the pattern of LEDs that need to be turned on and off to correspond to a digit, but at the moment this isn't actually an RGB value, it's just an on or an off, and it also doesn't say whereabouts in the strip this pattern should be placed. So that is the function of this setDigit command here. So it takes 3 parameters. Which of the displays in the strip are we currently trying to set the value of? So if this is 0, that's the closest display to the Arduino, and then it's 1, 2, 3, however many displays you want to chain together. What value do you want to set it to? And also, crucially, what color do you want this digit to be displayed on that value? And what it does is it loops over all of the LEDs in the strip, and it reads, it does a bit read command. So remember that this was a binary value we defined in the digits array up here, a binary value consisting of 32 bits, which are either ones or zeros, and then we're going to treat those as ons and offs. So it's going to read the pattern of ons and offs from that digits array corresponding to the value that we want to display. So if we want to display the digit 3, for example, it is going to read the pattern here. Whoops. It's going to read the pattern here that corresponds to the digit 3. And then it's going to set the value, the V property of the passed in color to be equal to that 1 or 0 value, so the on or off, multiplied by 255, which is the maximum brightness it's possible assigned to an individual LED. So the LEDs that corresponded to a 1 here are going to get assigned maximum brightness, and the ones at 0 are obviously going to remain at 0, which is the same as saying they're turned off. And then we're going to assign that color pattern there to the LED that we are up to in the strip. So we're going to loop over every LED in a digit, and we're going to apply an offset for the digit that we are looking at the moment. Let me try and explain that another way. So for example, the first digit in the strip we would pass in a value for display of 0 because we're looking at the first digit. So this is evaluating to 0 here, and we simply loop over each LED in the strip I. If we wanted to set a value of the second digit in the display, well then we pass in a value of 1 here, and we need to kind of offset our counting in the strip because we only want to start setting the value of the LEDs that correspond to the second digit. So what we do is we add on all of the LEDs that were assigned to the first digit, and we do that for however many preceding digits there were in the strip, and then we just start counting instead. And we assign the colour value for the second digit or the third digit or the fourth digit, however many you want. So what this does is it scans to the appropriate point in the LED array for the digit that we want to set the values to, and then it looks up the pattern corresponding to the value that you want to display, and it sets the brightness to maximum or to off, which corresponds to the value that needs to be displayed. Okay, that was a little bit hard to explain, but hopefully that made some sense to you. That's kind of the key function here that is going to translate from this pattern here into the appropriate values that we're going to send to the LED strip. Now the next functions all relate to the timer functionality. So when we start the timer, what we're going to do is we're going to change the state to active, and we need to keep track of the time now when the timer was started. So that's what millis gives us. That's the number of milliseconds since the sketch started running. When we stop the timer, well, we change the state to inactive, but that is the point where we keep track of this cumulative elapsed time that we've counted so far. So it's the current time minus the time that we started the most recent session of counting, essentially. And we add that to the cumulative elapsed time. When we reset the timer, well, again, we just put a little serial message. We set the state back to inactive, and we clear any elapsed time that we have kept track of so far. So hopefully they all make sense pretty much. So now we get onto the setup function. So setup runs once when the code first starts. It initializes a serial connection. That's just used for the little debug messages that we've been observing up here and here. That just keeps track of what's going on with the code. We actually initialize the fast LED library itself. So this is the add LEDs function. I mentioned if you're using a different type of LED strip, you might need to change the parameters that are supplied here. So this is where you would name the type of strip that you're using. Mine only has a single data pin. Some LED strips have a data pin and a clock pin, in which case you'll need to pass that in as well. But if you're using exactly the same as me, this is the function constructor you'll need to use. And we tell it the array of RGB values that we're going to send, and also how many elements there are in that array. Then we actually attach our debounce objects as well, and we're going to be using input pull-ups on all of them. So that's because when the button is not being pressed, we want that value to be pulled up to a high 5 voltage, and when the button is pressed, it's going to connect through to ground and read low instead. And we initialize the timer in the inactive state, so it's not going to be counting when it first starts up. It will just stay at 0. And then we go on to the loop function. So what we do in loop, well, the first thing we do is we always check whether any inputs have been pressed. So if you want to create any kind of controller that has input, it's really important to check your input as frequently as it's possible to do so. You don't want to miss any inputs because your code was busy doing something else or didn't check it this frame. So even if we're not going to take any action on those inputs, we need to update all of the bounce objects, which is just going to check whether any button has been pressed. We'll also grab the current timestamp, so that's what millis is going to give us here. We're going to use that in some calculations for the timer in a moment. And we'll create a new variable in which we're going to calculate the value that we want to be displayed. And I'm initializing the hue, so the color that is going to be displayed. We're actually going to change this value depending on the state of the timer a bit later anyway, but we'll give it an initial colour. Now, the way that the fast LED library works is that the hue value is somewhere between 0 and 255. This is a little bit confusing because generally speaking, hue is described as a value between 0 and 360 degrees. So if you look up kind of like an HSV converter on the web or something like that, you might find values that don't seem to correspond to the right colour when you look at them on an LED display. So the reason is because you need to scale them to values between 0 and 255 rather than 0 and 360. But you can find a graph on the Fast LED website which will show you what that corresponds to. And what we do next depends on whether we are currently counting or not. So if we are currently active, that means that the value on the display is changing. And if we are currently counting down, then we calculate what the value that should be displayed on the timer is by starting with the original duration of the countdown. We subtract however much time has elapsed since the last time we pressed the button, and we also subtract any cumulative elapsed time that had happened before that. And that will give us a value that is in milliseconds of the current time remaining. Then we need to work out what colour we want to display that value in. And again, I don't know if this came out very well in the video earlier, but I'm actually changing the hue of the time remaining based on how close we are to 0. So what I'm doing here is I'm mapping the hue from a value between 0 to 100 based on how much time is left starting from 0 and going to the duration. So when the amount of time remaining is very close or equal to the total duration of time, the hue is going to be 100, and that's kind of greeny. So basically, when the timer first starts off and we've got all of the duration of time remaining, it's going to be green. And I'm kind of using this to imply some kind of, it's okay, you've got plenty of time left with whatever task it is we're timing, that's why it's green. As the time gets closer to 0, however, the hue is going to get closer to 0, which is red. So this is just trying to, again, get some kind of sense of urgency. The time is approaching 0, so it fades from green to red as the countdown proceeds. That's what this line here does. When it reaches 0, now at this point here, maybe you want to add some code that, I don't know, sounds an alarm or triggers some kind of other event. But this is the code that is executed when the timer reaches 0 of a countdown. All I do here is to prevent the timer accidentally going into negative values. I force it to be 0, and then I just disable the timer from counting down any further as well. But you could add more code in here if you want. Alternatively, it might be that the counter is active and it's counting up. And in that case, we come here instead. Now, this is actually a bit more straightforward than the previous example, because here we had to subtract the amount of time that's happened so far from the timer duration. If we're counting up, we don't have a duration to worry about. So all we do is we add on the number of seconds that have elapsed since we started counting, plus any cumulative elapsed time, and then that is our simple value. And just for this example, I'm just going to force the hue to be 0, so that's just red. Nice and easy. Now we need to actually deal with some inputs. So if we are active and the start button is pressed again, we want to stop the timer. That's there. And that's the only input we worry about when we're currently counting. The left and the right buttons don't do anything when the timer is active. The only thing that happens is the start button. Then we go on to this section here. So the else if here corresponds to the if state is active here. So this whole section here was only being executed if the countdown is currently active. And then this section is what happens if it is not currently active. So what happens in that case? Well, this is the pulsating colour which I was trying to refer. So I've tried to give as many different examples of different ways that you can set the colour here. When it is counting up, we just set a constant colour here. When it is counting down, I am changing the value gradually based on the value that's being displayed. And when it's inactive, I'm just pulsating it over time. So this says to oscillate between a hue of 0 and a hue of 40. So that's going from red to kind of yellowy. And it does it at 20 beats per minute. So it's kind of a slow pulsation. Now, if we press the left button while we are currently inactive, that reduces any value that's currently assigned on the duration. So if there is currently some countdown value set and it is greater than a minute, we'll take a minute off the countdown. And then we'll also display that value. If the right button is pressed, well, that's kind of the opposite. That's going to add on a minute to the timer duration and then display that value as well. So that's how we set the duration that we want the countdown to start from. And then if the button is pressed, so this is actually how we start the countdown in the first place, and it does one of two things depending on whether the left and right buttons have been pressed first. So basically, if you start the countdown off and the timer is displaying 0, it's going to assume that you want to count up. So you're starting from 0 and it's just going to count up. If, however, you've pressed these buttons at all to set a duration that is anything other than 0, then it's going to count down from that value instead. That's the kind of the simplest way I could think of to have this two modes of counting up and counting down. If you wanted to, you can have a toggle switch instead that switch between the two modes, or any other method you wanted to. Maybe you want to double tap to count up and single tap to count down. But this was just how I thought was the easiest way to demonstrate it. So effectively, if the existing value is 0, it counts up. If it's any other value, it counts down from that value. And then it starts it. Now, up to now, all this code here has been calculating this time value, which is the value that we want to display, in milliseconds. And so the last bit we need to do is actually to format that into the appropriate format to put onto the 4 digits. And this depends on whether you included that define that was right at the top of the code here, whether you want to display as minute, minute, second, second, or whether you want to display as 4 seconds. And again, you could put in any other variations of that you wanted, really. But if you want to have minutes and seconds, what you need to do is to take your time value, which is in milliseconds, remember, divide it by 1,000 to get it into seconds, and then do a modulo 60 to work out how many remainder seconds you've got that are not a whole minute, essentially. Modulo means the remainder of a function. If we've got a multiple of 60 here, well, that's not a number of leftover seconds, that's a whole minute. So we want to ignore that. All we want to do is to find out how many seconds we got left over that haven't formed part of a minute. To find out the number of minutes we've got, well, in that case, we take the time value and we divide by 60,000 because that's the number of milliseconds in a minute. And it's an integer division here, so that's going to round down and give us the whole number of minutes. And then we set the digits based on those values we calculated. So the 3rd digit, or the 4th digit along, as it is, because that's the one with index 3, that's going to be the number of whole seconds. And then we've got tens of seconds, and then we've got minutes, and we've got tens of minutes. So that's if you want to display in minutes and seconds. Alternatively, if you just want to display it in seconds, you can ignore the 60s that are mentioned here because these are all conversions to minutes, and instead you can just divide by whatever value you want. If you wanted to show tens of seconds instead, for example, you could just divide by 100. Or by 10, or if you wanted to show it, in the complete resolution that it's being calculated in, you don't need to divide by anything at all there. So that's really up to you, the level of granularity and precision you want to show in the display. And then the setDigit function, so remember what setDigit does is it takes the pattern for each digit here, and then what it does is it converts that to a color value, and then it assigns that to the particular elements in the LED's array. What we then need to do, having done all that, is to actually send that array of values to the LED strip,
and that's what the fast LED.show method does. So that actually sends all our updated values to the LED strip and makes them change colour accordingly. And finally, I've just put a little delay at the end just to slow the code down, because we don't need this to run as fast as the processor is capable of running it. That's it.
So that just about brings me to the end of this video. I hope you found it useful or informative. If you have any questions or comments, do please write them below and I will do my best to get back to you. I also want to take this opportunity to say thank you so much to all my Patreon supporters as well, who enable me to create these video tutorials each month. I do really appreciate all of your support, so thank you so much. I will put a link to my Patreon page in the description as well, and if you're interested in finding out more about any of the projects which I've published in this channel, you can head on over there, where you can also download the code and wiring diagrams and other supporting materials for all of my projects. If you would like to, and if you are able to support me to create more tutorials in the future, I would obviously hugely appreciate that. But if you cannot or don't want to, don't worry, I will still continue to create these videos and upload them to YouTube each month for free anyway. Other than that, I just want to say thank you all very much for watching, and I look forward to seeing you next time. Okay, cheers, bye.